All right. So in this lesson, we're gonna go over optimization, and this is probably like the most applicable part of calculus you'll use in this chapter, and maybe even the whole course, because you can actually see real life problems that calculus is used for. And this is kind of gonna give you like a good sense of why you need calculus if you're going to study business or econ or even some social sciences. Because when you were talking about optimization, we basically want to figure out values of equations that will give us the most or the least profit, or maybe the most material. It just depends. And we call that optimization. So we find like minimum maximum values for certain scenarios. So when you're doing these problems, they are kind of tough at first because you really have to kind of be creative. There's not like a set of formulas that you can always use to start a problem or to end a problem. You really just practice in a bunch of different situations. But here's some guidelines to help you get going. So when we're doing optimization problems, remember we're trying to find minimum or maximums of of an equation. And so it's going to be helpful if you make a sketch and identify all the important quantities that you're working with. Then you have to find a primary equation, meaning that like an equation that you're going to be able to use all throughout the problem. And since we're only in one variable calculus, you have to find a way to make this primary equation in just one variable. So like, if it's like if you have like something based on length and width, you have to find a way to make length and width into like one form. Like in other words, you have to find the equation to just make it in terms of length, or find it in terms of just width. Then this is where we're going to apply the stuff we've learned throughout this chapter to figure out the local maximum, minimums, and critical values, because that's where we're going to use the first derivative test. And then based on what the problem is dealing with, and you're going to figure out like what values would make sense, what values would be appropriate in the domain. And let's go ahead, let's just get started, because it's always the best way to learn this stuff. So we're going to go over this problem here where we have a box that has a square base, and we want to basically find the dimensions of this box that will give the biggest volume, the maximum volume. So here we have again box. We already have a sketch of what the box can look like. So basically it's a cube. The square base, so then that means each side length of the base is, we're going to say it's x, and we're going to say the height of the box is h. And we're given a restriction. We're given that the box has a surface area of 108 square inches. So let's start with that. Let's make surface area S, and let's make that equal to 108. Now, if our box has, dimensions x by x on the surface, that h has the height, then surface area would be, the surface of the base, the area of the base which would be x squared, plus the areas of the sides. And so we have 1, 2, 3, 4. All four of the sides have a base length of x and a height of h. So we're gonna have basically plus 4 x h. We're given it right here. But again, the surface area, the area of the base, plus 4 times the area of the sides. And we're trying to find the maximum volume. So let's write that. Find max volume. So we want to come up with an equation for volume first. So let's make it volume in terms of V. And volume will be, length times width times height. It'll just be x times h, or x squared times h. Okay, so this is basically our primary equation. Now, see, if we could just, it'll be, the idea is if we can just graph this and look at the graph and see what the graph is doing, and then you can look where it has maximum, then we basically done. That's basically if we had technology and, later on, when you become an engineer. But for now, we don't have it. Let's just say we don't have any calculator, and we can only work with one variable. So if we got to get rid of this x or get rid of this h and make it into the whole equation in terms of x. So the way we do this is that we have, see, this equation that's in terms of x and h. And since we have two equations, we can basically solve each equation for x and h and rewrite one equation for just in terms of h and the other in terms of x. So what I'm going to do is solve this equation here for h. So I'm going to have 108 minus x squared equals 4xh. Solving for h, divide both sides by 4x. So those cancel, and then what I get is that h is just going to be 108 over 4x. I can basically say that's 27 over x minus x squared over 4, or you can say minus x over 4. Now with that, I rewrite this equation as x squared times this quantity times 27 over h minus x over 4. Clean that up again, and I can get a volume equation. Let me distribute that. So no, whoops, not 27 over h, 27 over x. What I meant to write. Okay, volume is 27 x, x squared over x cancel, minus x cubed over 4. Or this will actually be 27x minus 1/4 x cubed. Now the problem, it becomes much simpler because we have an equation for volume and it's just in terms of one variable. So, if we can find where the maximum value of this equation is, then that can basically tell us what the maximum volume will be. And we can figure out what the x value is at that, what the x value is at that maximum volume. So I basically want to work with this equation, kind of like what I did in this throughout this whole chapter. I want to find the maximum of the relative extrema. In this case, I want to find the maximums. So I'm going to take the derivative, find the critical values, and then study those critical values, see what those critical values give, like see if those give you like the minimum, maximum, and so forth. So let's first differentiate this. So we have, let me write it as dv, the volume in terms of x, dv dx is just going to be 27 minus 3/4 x squared. Now find the critical values here. So set this equal to 0. 0 equals 27 minus 3/4 x squared. Solving this, 3/4 x squared equals 27. I'll get them 9 times 4, x squared is 36. And then that means my critical values would be x equals 6 and x equals -6. So I want to see basically what values of the volume these x values give. Now here's the thing. In this context, if we're talking about real life, the box, you're not going to have a negative, x value because you're not going to have a negative, length. So we don't even got to check this one. Let's check x equals 6. Let's see what we get for that. So the volume here will be basically 6 times, what was our equation for volume? So right here, let's see, let's plug it in here. Volume be 27 times 6, not 27. Yeah, 27 times 6 minus 1/4 6 cubed. And we get 27. Should get I'll get 108 inches cubed for my volume. Now here's the thing. How do we know if this is going to be the act maximum? How do we know it's not content? This is not like a minimum. Just to make sure you don't get like a incorrect answer based on something like that, based on kind of like a tricky mistake here or a trick problem. Just check the behavior before and after this, or you can basically check the second derivative here. There's a couple different ways to do it. So if you check the second derivative, if it's concave down here, then that means that this is going to be a local maximum. If it's concave up, then this is local minimum. So a couple different ways you can do this. So let me do that. Let's check the second derivative. The second derivative of v with respect to x. And that will just be 2 times 3, -6. -6/4 x. And if x equals 6, then the second derivative is going to be negative. So again, it's not necessary to find the exact value, just figure out the sign. So then we know this is going to be a local maximum at when x is 6. So then this is definitely going to give us our maximum value. Now, kind of give you some more insight, just to kind of make sure we understand what this is actually doing. Let's look at an actual graph of this problem. So so remember this. Make sure you recognize that we're trying to figure out what's going on with the volume. So here's an equation of the volume. So you can see that it starts increasing up to here, then decreases afterward. And if we were to analyze this for the maximum, we can't get any values that are negative. So let's start like 0. Then you can see how there's a maximum here. See that this is the graph of the volume, and the volume has a maximum when x is 6. So again, this is just something to help you better understand this problem, because it's always good to have a visual. But of course, you want to be able to, you want to do this if you want to go through all this work if you had a graph of it. But on your AP Calc exam, there will actually be problems that are going to be more about analysis versus, doing it by hand. So make sure you can make the connection here.